Hello everyone and welcome to MV Tutors. While you are here, please don't forget to like our videos and also subscribe to our channel. Please do spread the word to your friends who are also in matric and those who are also upgrading. Alright, let us look now at the chemistry paper, question 1, and just refresh our minds as to what's happening. For those who just started with matric this year, obviously you're limited in some of the questions, so I believe organic chemistry you've done, so you can follow. All right, until you get into further depth. All right, so question 1, multiple choice. Let's make that a little bit bigger. Okay, yeah. So question 1.1, it says, which one of the following terms describes hydrocarbons that only contain single bonds? Remember, there are single bonds, double bonds, and triple bonds. Yes, and the ones that are double bonded or triple bonded, they are unsaturated, but the ones that are single bonds, they're actually saturated. Okay, so we're going to go with option B. Let me just write there. We are on question 1.1 is B. And then 1.2. Which one of the following combinations correctly indicates the strongest intermolecular forces found in ethanoic acid and methylpropanoate respectively? So ethanoic acid is a carboxylic acid, and because of that OH group, that hydroxyl group, we get hydrogen bonding. Then we get methylpropanoate. Okay, methylpropanoate consists of methanol and also propanoic acid, but together they make the ester. So by themselves, the alcohol and the carboxylic acid, they have hydrogen bonding, which is very strong. But together now, when they form an ester through the condensation process, the whole product doesn't have hydrogen bonding anymore. It's not as strong anymore. So with ethanoic acid, we're looking at hydrogen bonding. Okay, so the options are A, C, and D. For methylpropanoate, we're not looking at, unfortunately, it's not hydrogen bonding. And London forces are quite weak, so D would be the correct answer where we have a dipole-dipole force. Okay, so your answer then would be D for 1.2. Okay, these are the physical properties that you need to look at. We do have lessons on that. If you go to our playlist and look at the chemistry folder, you'll get them. All right. 1.3, a test tube contains a liquid hydrocarbon. Remember, with your hydrocarbons, either alkenes, alkynes. Okay. When bromine water is added to the test tube, the mixture decolorizes immediately. Okay, now we have a halogen and we have a hydrocarbon. So, I don't know, hello alkanes are calling our name? I don't know. Which one of the following combination correctly identifies the compound and the type of reaction that takes place in the test tube? Okay, so compound, do we then have hexane? Is it an alkane or is it an alkene? Okay, here's the thing. If you have a hydrocarbon and then you add to it, it can't be an alkane unless if there's some substitution reaction going on. You know, alkanes are fully saturated. Okay, so I'm thinking it's somewhere along the lines of an alkene. The double bond that can be broken, added to, I don't know. So I think I'm gonna just ignore options A and B. Let's go to the alkene. All right, so hex 2-ene. And then what type of reaction I'm gonna have? All right, so if you're gonna add to a double bond, you're gonna get a single bond, so it could be an addition reaction. Substitution reactions are more common for alkanes. So are we good with option C? Are we? Yes, let's go with option C. All right, and then 1.4. Which one of the following statements is the correct definition of the rate of a reaction? Okay, 1.4 is no longer organic chemistry. I'm so used to 1.1 to 1.4 being organic chemistry. They changed things up a bit. It's okay. It's all right. We can go to the rate of reactions. All right, so is it A, the time taken for the reaction to take place, No, it's the rate at which the reaction takes place. So you do record the time so that you see, is it fast, is it slow, but not just the time taken. Okay, so A, not quite. B, the speed at which the reaction takes place. Tempting because now you're asking yourself, is it slow or is it fast? But speed, not quite, not there. Okay, and then 1.4 C, the rate of change in concentration of the products or reactants. Yeah. We're almost there, we're getting there. Sounds correct. D, let's just make sure. D, the rate of change in concentration of the products or reactants per unit time. Okay, so the actual answer would be C in this case. It is the rate of change in concentration of the products or reactants. And there is a time, the fact that we're saying rate means that time is already factored. So the difference between C and D, if you say per unit time, the fact that you said rate, it is per unit time. So now you're saying per unit time, you know. So I know D is the one to go for, but C is the correct answer. 1.5. Consider the balanced equation for the reaction between magnesium powder and excess dilute hydrochloric acid. So there it is, and we have a result of a salt and hydrogen gas. Which one of the following will not increase the rate of this reaction? This is where your theory comes in for rate of reaction. If you have forgotten, please do visit our playlist. Go to the chemistry playlist and go look at the rate of reactions. Okay, so which one of the following will not increase the rate of this reaction? Is it A, increasing the volume? Okay, B, increasing the temperature definitely increases the rate. C, increasing the concentration definitely increases the rate. Sorry for the noise outside. And D, adding more magnesium powder, yeah, it will definitely increase the rate. Okay, so A is the one that will not increase the rate of this reaction. So 1.5, A. Two identical sealed gas jars, this is now 1.6, R and S initially contain gases as shown below. So for the gas jar R, you have hydrogen gas as well as iodine gas. And then for gas jar S, you have 2 moles of hydrogen iodide gas. Now equilibrium is reached in both gas jars at 500 degrees Celsius according to the following balanced equation. So, and remember gas jar R, we have both hydrogen gas and iodine gas. And we can see through this equation that at the end of the day, you're going to have 2 moles of hydrogen iodide. And then at the same time, gas jar S already has 2 moles of hydrogen iodide. So, man, it's the same, okay? What's one? So now, which one of the following statements is true at equilibrium? A, S will contain 1 mole of iodine gas. B, R will contain a large amount of iodine gas than S. R and S will contain the same amount of hydrogen iodide. Sounds more like it. And D, S will contain a larger amount of hydrogen iodide gas than R. No. Okay, so the correct answer then for 1.6 would be C. It's pretty much the same thing. Okay, so 1.6 is C. Now let's move over to 1.7. Which one of the following salts, when dissolved in water, will not change the pH of water? This is where now theory comes in. Okay, yeah. So let's have a look at the options that are given. Okay. Which one will not change the pH of water? Is it going to be sodium carbonate? Is it going to be COO? I'm not sure what that is. Sodium, will it be ammonium chloride or would it be sodium chloride? What do you think? I think in all of those, what makes sense for me, because I'm familiar with it, would be sodium chloride. Okay, so 1.7, the answer for that would then be D. But like I said, read up on this, okay, and you will know which one wouldn't change the pH of water. Okay, and I say that because pH of water, it should be 7. It should be balanced between an acid and a base. If you're going to add a carbonate is basic, so it's going to make it more basic. If you add COO, sounds like some acid actually, so it will make it more acidic. And then if you add ammonium, which is like, geez, I forgot, is it a base or an acid? But I think it's a base. So in that case, yeah, the pH will change. But sodium chloride, it's neither an acid nor a base. So it just keeps it as it is. It will not change the pH of water. Okay, I think that's more of an acceptable answer than saying just sodium chloride. Okay, 1.8. So a dilute acid is titrated against potassium hydroxide solution. Okay, this is quite a strong base. Yeah. At the equivalence point, the pH is 7. So you have this dilute acid. Even though it's dilute, it's quite strong, because a strong acid and a strong base will give you at that equivalence point a pH of 7. Okay. Which one of the following combination correctly identifies the acid and the most suitable indicator for this type? For the titration, sorry. Yeah, like I said, it must be some strong acid that we have there. So the first two acids, not so strong. No, as soon as you have a carboxylic acid, it's not really strong. So I would go with option C or option D. Strong acid and a strong base gives you a pH of 7. They balance each other out. So C and D, or C or D are the options. Now let's look at the indicators. Will we have an indicator of phenolphthalein, or will we have of bromothymol blue? Okay, again, theory. This is something that you should know, and as such, the answer would then be D, which is bromothymol blue. Okay, and then 1.9, we're almost there. Which one of the following statements is true for an oxidizing agent? Please do not confuse an oxidizing agent for something that is oxidized. No, an oxidizing agent has been reduced. Okay, and what happens when a substance or whatever has been reduced? It basically gains electrons. Okay, so it says which one of the following statements is true for an oxidizing agent? A, it gains electrons. B, it causes another species in the reaction to be reduced. Itself, it is reduced. Okay, it causes another one to be oxidized. Okay, C, its oxidation number does not change during a chemical reaction. No. Last one, D, its oxidation number increases during a chemical reaction. No. So the answer there would be A. And then we're done. Almost there. Which one of the following metals will reduce cadmium to plus to cadmium solid? Okay, interesting. But, so it will reduce it, but will not reduce manganese to plus to manganese solid. In this case, you're going to have to look at your tables and have a look between zinc, silver, nickel, and magnesium. Okay, let's remember all of that. Let me just write them down. So this is cadmium. Okay, we need to see where cadmium is. And then silver, nickel, and magnesium. Let's go and check out the tables. And then we can be able to tell. I don't know which table you prefer. Let's start with the first one. Okay, why not? So for silver, okay, so I see cadmium. We're looking for cadmium. We're looking for silver. There is silver. So silver we get positive 0.8, and then nickel. I hope I don't miss anything. So looking for nickel and magnesium, as well as cadmium. I see cadmium 2 plus, it's negative 0.4. And then nickel and magnesium. Magnesium, I see it, it's negative 2.36. Okay, now nickel. I must have missed. Oh, nickel is negative 0.27. All right, let's go back to the question. Now I forgot what they have asked. Okay, let's do this. Yeah, 1.10. Why did they have to make us go to the table? That was just going to be a straightforward one. Okay, which one of the metals will reduce cadmium 2 plus to cadmium, the solid, but will not reduce, snap, we forgot manganese. Okay, here we go again. I forgot about manganese. Let us see. Okay. You guys can just skip and go to the end if this process is just too laborious for you. You know it's 1.18. Negative 1.18. Okay. Alrighty, here we are. Let's read it one more time. Which one of the following metals will reduce cadmium 2 plus to cadmium, okay, but will not reduce manganese? All right. Gosh, I forgot zinc, but I think zinc is negative 0.77. I think I've used it so many times that, yeah. So if I look at cadmium, it is negative 0.4. Anything in the positive will not reduce it. Okay, we're looking at things that are in the negative. So we're not going to look at silver, but we're going to consider zinc. It's smaller than cadmium, so that's an option. Nickel, not so much, it's larger. So anything larger than negative 0.4 will not work. We're looking for something that is smaller. So magnesium is also an option. Okay, but it will not reduce manganese 2 plus. So manganese negative 1.18. Magnesium will definitely reduce manganese, so unfortunately it falls off. What am I doing? I'm putting a star there. So magnesium was in the running, but we don't want it to reduce manganese. So magnesium can reduce both cadmium and manganese, but it will not work here because we're looking for something that will reduce cadmium but not reduce manganese, and that is zinc. Yo, last question. Why are you taking us so long? But sorry about that. But yeah, we are done with question 1. Hello everyone and welcome to MV Tutors. I'm Tila and I'll be looking at organic chemistry with you guys. So that's question 2, 3, and 4. Okay, so without wasting any time, let us go straight to question 2, 2.1.1. So A to F in the table below represents 6 organic compounds. So we have A over there. I would have said it's an alkane, but I see a bromine atom there, so it's a haloalkane. Then we have B. There's a triple bond, so it's an alkyne, right? Is there a branch there? Probably. C, we see there's a double bond to oxygen at the end, so we're looking at an aldehyde. D, we have a double bond to oxygen, but it's somewhere in the middle, so we're looking at a ketone. E, I see Cu, so it's a carboxylic acid, and F, I see OH, a hydroxyl group, so an alcohol. Okay, we're ready to answer these questions. Now, 2.1.1, write down the letters that represent 2 organic compounds that are isomers of each other. Did you notice them? C and D, we have an aldehyde for C. All right, first of all, we have 4 carbon atoms. You can see that for both C and D, right? But for C, we have an aldehyde, and for D, we have a ketone. So they are definitely isomers of each other. Okay, so we can simply say C and D. All right, 2.1.2. Write down the type of isomer or isomers that we identified in question 2.1.1. Well, they are, or they have the same molecular formula, but they are in different functional groups, so they are functional isomers. Okay, so the type of isomer we have, functional isomer. 2.1.3, write down the general formula of the homologous series to which compound B belongs. Let me just take it down a bit. So that triple bond gave it away, right? It is an alkyne, right? Alkane, alkene, alkyne, triple bond alkyne. And the general formula for it will be CN H2N minus 2. Remember, if it's plus 2, it is the alkane. If it is just 2, it would be the alkene, but the alkyne is minus 2. All right, so now 2.1.4. Write down the name of the functional group of compound F. Please don't confuse homologous series. I had another pronunciation. It's homologous or yeah, let me not even go there. I'm just gonna say homologous. Some say homologous. Yes, that's the one. Homologous. So I don't know if you're on the team of homologous or homologous. Whatever floats your boat. So there's a difference between functional groups and the homologous series, okay? And sometimes it can be a little bit confusing, but please, if we're referring to the homologous or the homologous series, we would definitely say it's an alcohol, but the functional group is the hydroxyl group. Okay, I hope that is clear. Hydroxyl group because of the OH there. All right, and let us now go to 2.2. Question 2 is quite lengthy, so please make sure that you gather your marks here. Write down the IUPAC name of compound A. You know you can't run away from these, right? So we need to look for the longest chain. And, okay, I'm going to put it on a straight chain so that we can figure out what's going on. So I see 1, 2, 3, 4, 5, 6. Okay, I'm not going to put the hydrogens there. It's going to take quite a while. So the first one, the second one, and on the third one, we have 2 branches on either side. Okay, and then the 1, 2, 3, and then the fourth one. Okay, it's just one H and a bromine atom there. Then the fifth one, please don't let it confuse you when it starts bending. Okay, then the fifth one and the last one. Okay, my question is, where do you start numbering? Do you number closest to the bromine atom or do you number closest to the branch? Well, you're going to number closest to the branch, okay? But how do you then pronounce, how do you write it down? Are you going to start with the branch or are you going to start with bromine? Well, you're going to start with the one that comes first on the alphabetical order, and that will be bromine. Okay, so I'm going to start numbering this side. 1, 2, 3, 4, 5, 6. So it will be 4 bromo. Okay, and then 3, 3 dimethyl. Some say dimethyl. And then how many carbon atoms are there in the longest chain? There are 6. So 4 bromo, 3,3 dimethyl hexane. So this is a haloalkane. Okay, cool. This is 2.2.1. 2.2.2. Compound B. Okay, so we know that it is an alkyne. But yeah, let's also just put it in a straight chain. You know, sometimes it's better and you see things much clearer when they're in a straight chain, unlike when there are some bends and. So on the second carbon, I'm seeing a branch. Okay, one, two branches. Okay, yes, 2 branches. Then another carbon, and it has a triple bond. Then we have, see over there. Okay, then 1, 2, 3. Okay, so the longest chain I see here, 1, 2, 3, 4, 5. Oh, where do we start numbering? Do we start at the branches or do we start at the triple bond? We'll start at the triple bond. So we have 1, 2, 3, 4, 5. Okay, so this is an alkyne, all right? Yeah, so how are we going to number it? We're going to have 4,4 dimethyl. Okay, 4,4 dimethyl hept, no, 5 pent, sorry, pent 2 ine. Okay, really this is where you should be scoring your marks. Okay, now we get to 2.2.3, which is compound C. We have spoken about this. It's an aldehyde because the double bond to oxygen is at the end, and we have 4 carbons, so it's going to be butanol. And here you don't need to indicate the number. Butanol, Al for aldehyde. And then 2.3. Alright, compound F reacts with a carboxylic acid to form compound S in the presence of a strong acid. What is compound F? I remember it was an alcohol. So it's butanol, right? And it reacts with a carboxylic acid to form compound S. So compound S is an ester. Okay, so now 2.3.1. Write down the name of the reaction that takes place. You can either say it is called esterification. Okay, esterification. Or you can say it's a condensation reaction because while an ester is being formed, water escapes. Water is one of the products. And then 2.3.2. So compound S has an empirical formula of C3H6O. Remember, an empirical formula is the simplest it can be. You cannot simplify it any further. So we have an empirical formula and a molecular mass of 116 grams per mole. Write down the molecular formula of the carboxylic acid. So compound S is the ester. Remember, an ester and a carboxylic acid, they're actually functional isomers. So if we have the empirical formula of C3H6O, what is the molar mass of this empirical formula? Okay, so I'm going to say molar mass of the empirical formula is 3 times carbon, and carbon has a molar mass of 12, and then we have 6 times hydrogen, which is just 1, and then plus oxygen, which is 16. Okay, so 3 times 12, I forgot my calculator, 36 plus 6 plus 16, so 36 plus 6 is 42, plus 16, 42 plus 16 is 58 grams per mole. If I calculated this incorrectly, please write it in the comment section. Alright, so now we're not done. We need to get the molecular formula for the carboxylic acid. Remember, they gave us the molecular mass, which is 116. So if I then take 116 and I divide it by 58, I'm guessing it's 2, right? Because 58 times 2. Okay, so we get 2. It can't be 3. Okay, so we get 2. What does that mean? It means that your molecular formula is twice that of your empirical formula. Right, so you have C3 times 2, which is C6, H6 times 2, which is H12, and O2. So our molecular formula is C6, H12, and O2. But remember, this is for compound S. It is for the ester. And in order for this ester to be about, we had compound F as one of the reactants, which is butanol. So the carboxylic acid here, if butanol has 4 carbons and your total compound or your total ester compound has 6 carbons, it means that your carboxylic acid has only 2 carbon atoms. Okay, so we now, for molecular formula for carboxylic acid, will be C2 first and foremost. And then your alcohol has how many H's? It has 3, 4, 5, 6, 7, 8, 9, 10. 10 H's. What will your carboxylic acid have? Actually, you know what? Let's do this. Carboxylic acid is pretty much C, and then you have C, double bond. Okay, we're remaining with 2. So let's not make life hard for ourselves. So this is the carboxylic acid that remains. Remember, this is compound S. Your carboxylic acid, what do they want? They want the molecular formula. You have C2, all right, H1, 2, 3, 4. So H4 and O2. That is simply the carboxylic acid, and we're done with question 2.
Well, hello there. Well, it is night over here where I am, and I'm from a school from educating the youth. So this is the only time I have to record this. But we're still in the 2022 paper 2 physical science. Okay. So now we are doing question number 3 together, and let's just get right into it. Oh, and before we do that, please like and subscribe to our channel. Would really appreciate it. Now, it says the melting points of some organic compounds are given in the table below. Okay, I can see them. There we go. The first question is, to which homologous series do the above compounds belong? Well, if you've done your studying well enough, you will know that actually all of these, just look at the last on. These makes them ketones, right? These are ketones. All right. Now the next question says the melting points of compounds ABC, so ABC, are compared. Okay, write down the control variable for this comparison. Well, the only thing really when you look at all of these things that's really consistent is that all of them are pretty much just ketones, right? So rather the functional group is what's constant amongst them. So we're gonna say 3 point where are we, 3.1.2. we're gonna say the functional group is the one. Functional group. Okay, so the functional group is the one that is pretty much controlled with these. No, I don't see anything else. Okay, let's look at 3.1.3 now. It says the melting point of compounds C and D are compared. Now let me ask you something. Which one has the higher energy? Which one has the higher melting point between these two, C or D? If you said C, then you are correct because these values are negative, which means the less negative is the higher the temperature. Okay, anyway, fully explain the difference in the melting point of these two compounds. Okay, I want us to do this systematically. First, let's pick one of them. Let's pick pentane 2-on. Okay, looking at pentane 2-on, comparing it to methyl butane. Remember, pent is a bigger number than but, so pent is actually 5. So when we look at the structure, okay, we can see that structure-wise, the pent is actually, it has a longer chain. Okay, so it has a longer chain. And then what does that tell us about the forces? Okay, the intermolecular forces. Okay, it has more forces. It has, since it has um, a longer chain, it has more forces involved in there. So what we can say then is that it has more, let's call them van der Waals. Van der Waal, more van der Waal forces to break. Okay, there are more forces to break because of the long chain. So what does that say about energy? It means there's more energy required. Okay, so there's more energy required to break down these forces. It's required, okay, to break down these forces. Okay, to break down these forces. All right, therefore, it has, therefore, pent, pent, 2 has a higher melting point. Higher melting point. Just like that. And we are done. All right, so let's do 3.2.1. Let's read 3.2. It says the table below shows the results obtained from an experiment to determine the vapor pressure of different straight chain primary alcohols at 300 kelvins. So the first, also there they are the alcohols in there. They are different vapor pressures. So it says define the term vapor pressure. Okay, so the first thing you need to understand about vapor pressure is that it really works in a closed system. Okay, and also it works in equilibrium. All right, so when we define it, we are going to define it as actually the pressure. Okay, the pressure, or is that how you spell pressure? Yeah, sometimes these are spellings. Exerted by, okay, a vapor. Remember, I told you it has to do with equilibrium. So it's a pressure exerted by a vapor in equilibrium, or let's say at equilibrium. At equilibrium, okay, in a closed system. Those are the two things I needed you to remember: closed system and at equilibrium. Just like that. All right, so let's do 3.2.2 now. It says write down a suitable conclusion for this investigation. Now, if you look at the alcohol here, we can clearly see that as we increase the carbon atoms, C1, C2, 3, 4, 5, 6, what's happening to the vapor pressure? It's actually decreasing because it started at 16, 7, 2, 0 0.9, 0 0.8, 0 0.1. So it's really decreasing. That's our conclusion then. Therefore, so we're gonna say as the carbon atoms increase. That's our conclusion. The vapor pressure decreases. So they really have an inverse relationship. It decreases. That's it. The next question is 3.2.3, and it says write down the IUPAC name of the alcohol with the highest boiling point. Okay, the highest boiling point is C6, and that's a hex. Remember, 5 is pent, but 6 is a hex. Because it's an alcohol, it's a hexanol. It's a hexanol. That's it. Okay, let's look at the last question now. It's 3.2.4, and it says the experiment is now repeated at 320K, which is above 300. That means we've increased the temperature. Will the vapor pressure of each compound increase, decrease, or remain the same? Now, if you heat up something, if you heat up water in a kettle, what happens the more you increase the temperature? Does the vapor pressure increase or decrease? That's what the question is asking. And if you said increase, then you are certainly right. It will increase. You've done this, you've seen it. That's what happens to pressure, vapor pressure especially. When you increase, they have a direct relationship. There's a direct relationship between temperature and vapor pressure. That's why it increases. Well, that's it for me. This was a very short question, and it is done.
Hello everyone, welcome back to MV Tutors. I'm Tulu and I'll be looking at question 4 from the chemistry paper, okay, where we have organic reactions. Should be an interesting one. Let's have a look. So it says the flow diagram below shows how compound A can be used as a starting reactant to prepare two different compounds, which is compound B and compound C. Then we have some reactions shown by 1, 2, and 3. Okay, so let's see what we can do with all this information. Before we even answer, can we just have a look at what compound A, B, and C is? Just draw the structural formula, especially for those who are visual learners like me who want to see exactly what's going on. Because if you have compound A as a condensed structural formula, you have an idea, but it's a little bit tough. Then you have compound B, which is like a molecular formula, and you're like, what is going on? And then compound C makes it even worse. So let's just try to draw. And we can see we have major products for both compound B and C. Okay, so let us look at compound A. Okay, by the way, this is question 4. So compound A, I'm just going to draw. We have the first carbon with its hydrogens. I'm not going to draw the hydrogen atoms out. It's going to take some time. And then we have the second carbon, which has a branch. You know, when we have anything in brackets, okay, let me not say anything, but in this case, what is in brackets just represents a branch. And then we also have a bromine atom, so we're looking at a haloalkane probably. Okay, and then we have the fourth carbon with its hydrogens and the last carbon. So we have what? We have a 2-bromo, 2-methyl butane. Okay, we have a haloalkane. Simply put, for A. And then B, after reaction 1 occurs, we have the compound which is C5H10. So is it C5 as in all the carbons are in a straight line and 5 of them? But because we have C5H10, I can see that the formula there is CnH2n, which means we have an alkene. Okay, and that alkene is a major product. So we still have our 4 carbons over there. Okay, and then we still have our branch. Let me just put it at the bottom. All right, but we have a double bond. Now my question is, we started off with how many hydrogens? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We started with 11 and now we have 10. Okay, so that tells us that we have removed a hydrogen and we have removed a bromine atom. So on this second carbon, a double bond will form. Now, we can either have a minor product or a major product. Okay, a minor product will yield a double bond on the first carbon. And why do I say that? How do we know which one is the major product and which one is the minor product? So whenever we have elimination reactions, please refer to Zaitsev's rule. Zaitsev, if you haven't heard of him, I think it's like this. I might have the spelling incorrect, but that's Zaitsev. So we're going to refer to Zaitsev's rule. When it comes to elimination reactions, when you have addition reactions, we refer to Markovnikov's rule. But in this case, for the major product, you are going to put the double bond at the carbon with the least hydrogen. So if you look at carbon number 1, okay, here, it has 3 hydrogen atoms originally. If you look at carbon number 2, it has neither. So that is where you're going to put the double bond. All right. But if they were looking for the minor product, you would have put it in the first carbon. So the double bond goes there. Okay. So let's just finish this off. At the end of the day, we need to have 5 carbons, which we already do, and 10 hydrogens. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So great. We have C5H10. That's B. And then C, now we have compound C, okay? And we still have the 5 carbons. So 1, 2, 3, 4, and we have 5. I'm just going to continue putting it at the bottom. Now we have, first of all, we have 12 hydrogens and we have an oxygen. So that tells me that we have an alcohol. This is an alcohol, but now the question is, where will the major product be? So this is an addition reaction. And as an addition reaction, we refer to Markovnikov's rule. Markovnikov's rule. Please go and read that in your textbooks, okay? This is applicable to the addition reactions. Okay, addition reactions. Whereas Zaitsev's rule refers, it's more applicable to the elimination reactions. Elimination. Okay. Elimination reactions. Okay, cool. So now we have an alcohol. Okay. These are not bothered. You have your hydrogens. You have your hydrogens over there. So where will the major product be? Will your OH group be on the second carbon, or the third carbon, or the first carbon? Okay, what does Markovnikov's rule say? So using Markovnikov's rule, we are going to have the OH group, the hydroxyl group, on the second carbon. Okay, so I hope you understand. Zaitsev's rule applies to elimination reactions, Markovnikov's rule to addition reactions. Okay, now we can answer the question. I've taken so much time to explain what's actually happening here, so I hope we are going to breeze through these questions. So 4.1, is compound A primary, secondary, or tertiary haloalkane? Wow, I actually thought primary, tertiary, secondary applies to alcohols only. But actually, I guess it does also apply to haloalkanes. So if we look at where we have our halogen, which is your bromine, the carbon it is attached to do you see that it is attached to other carbons? There are 3, okay? So it's attached to 3 other carbons, therefore it makes it a tertiary haloalkane. Now, if we're going to give a reason for the answer, we're going to say that the halogen, okay, or the functional group is that the carbon that contains the functional group is attached to 3 other carbons. Or bromine, the carbon that is attached to bromine, or the carbon that bromine is attached to, is also attached to 3 other carbons. Okay, you can make up a story. You'll go on with it. I'm not going to write that down. You'll write that down for yourself as long as you understand. Okay, the whole thing here is not to cram, but to understand. Okay, now 4.2.1, consider reaction 1. That is where we have compound A, then the reaction, and then you have compound B. So it says, besides heat, write down the other reaction condition needed. Okay? In this case, you need a strong base. Okay? Yeah. I would say you need a strong base. An example for that would be, if you look at group 1 elements, you can go with sodium hydroxide or potassium hydroxide or lithium hydroxide. So yes, you do need a strong base. And then 4.2.2, write down the type of reaction that takes place. Well, I have already said it, but if you don't recall, remember here we removed hydrogen and a halogen. Okay, so we removed hydrogen bromide basically. And if you're removing that, because we had an alkane, even though it was a haloalkane, you can't really add to it. We didn't substitute, but we eliminated. So it's an elimination reaction. Okay, and then 4.2.3, it says, using structural formulae for the organic compounds, write down a balanced equation for the reaction. So we did put in some form of structure. I am going to copy and paste, but we're going to write out everything. Okay, so let us copy there with our limited space. We'll see how we work that out. Maybe let's make it a bit smaller. So yes, let's put in the hydrogens there. So you have your haloalkane over here with the hydrogens and your carbons and the bromine atom. Okay, so that's what you had initially. And remember that strong base. Let's just, let's choose sodium hydroxide. It could be anything. It could be potassium hydroxide. It could be lithium hydroxide, as long as it's a strong base. And we recognize strong bases with the hydroxyl group to it. Okay, that's how you recognize them. If it's like your carbonates, those are quite weak. Actually, this strong base, when you add to it, it's concentrated. I should have actually put in that part there. Even if you said strong base, that's fine, but concentrated base, that's also concentrated base, that's also, applicable. All right, strong base, concentrated base, yeah. So yes, and then what is our solution over there? So yeah, we had that, and then now we have compound B, which we did draw out. So let us just copy and paste yet again, because we did put in the work. Okay, copy. Okay, it won't fit there, but I'll just put it on the side. And yeah, just remove this calculator somewhere far. Okay, so our solution then, remember we should have C5H10. So hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And remember, there was this bromine atom. Okay, so let us not forget the other compound that formed. So it will be bromine Sodium chloride. So yeah, maybe let's go with sodium bromine. Okay, because there's that sodium there and the bromine, and you have a hydrogen as well as OH. So another product that we shouldn't forget is water. Okay, plus H2O. Oh, but they said they want it in a structure, so my bad. Let's put everything in a structure. So we have sodium and the bromine plus H2O. So we're going to have O with the H and the H. Okay, but the main product that we're really focused on, which is product or compound B, is that. So as long as you have that and as long as you have compound A, I guess maybe the others, they won't be so strict about putting it in a structural way. All right, and now that's 4.2.3. Now we need to go to 4.3, and it says consider reaction number 2. So that is where we go from compound B to compound C. All right, so it says write down the structural formula of compound C. We had already started, so let us not waste any more time. Let's just copy and paste. Absolutely nothing wrong with that. Okay, but obviously in your test script, you can't go and copy and paste. You can just copy. Okay, it's getting dark out there. All right, so we have the hydrogens. We need to put them in because they want the structure. Remember, you have your alcohol over here and you have your methyl group. Okay, butanol, butan 2-ol, or 2-methyl butan 2-ol. All right. Oh, and then that's 4.3.1. Now 4.3.2. All right, so they say write down the name or formula of the inorganic reagent needed. Okay, so what would be this inorganic reagent that is required? Well, in this case, sorry, I meant to put there 2. The inorganic reagent that we need here is H2O, or simply put water. And then now 4.3.3, the type of addition reaction that takes place. Okay, so remember we had our double bond over here for compound B, and we have our inorganic reagent needed, which is water, okay, which then broke the double bond back to a single bond, as we saw in compound A, something similar, but now we have an alcohol. So the type of addition reaction that takes place would be hydration, because you hydrated it, okay, with water. So hydration would do. Alrighty, and then 4.4, are we almost there? Yes, we are. So 4.4, consider reaction 3. Oh, that is when we go from compound A to compound C. Almost forgot about that. So now it says write down the type of reaction that takes place. Now, if you look at compound A, okay, if we were to write the molecular formula for it, we have C5, ne? And then H, I think we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, H11, because of that bromine. Okay, so it's a haloalkane. And we go back now to compound C. Compound C has C5, H12, and O. Okay, so instead of the bromine atom, we have an OH atom, which or rather tells us that it's an alcohol. So now let's go back to 4.4.1. It says write down the type of reaction that takes place. If you go from a haloalkane to an alcohol, what would have happened there? Okay, what do you think? I'm thinking along the lines hydrolysis. Okay, so if you are adding water there, it is hydration, but from a haloalkane to an alcohol, you didn't eliminate, you did not add, but you substituted. So it's a substitution reaction, which is called hydrolysis. So I think even if you said substitution reaction, I think that would be fine. So hydrolysis or substitution, okay, that is super substitution. And then we're almost at the end, 4.4.2. Besides heat, write down the other reaction condition needed. So what is required then for hydrolysis? Okay, in this case, we need remember for 4.2.1, we required a concentrated base. Here we're going to need a diluted or dilute base. Okay, and that base must be strong. I think that's very important. Okay, because if you have any base, it could be a carbonate. We don't want carbonates. It could be what else? What other weak bases are there? Yeah, it could be some weak base. So let's just make it clear. It is a dilute strong base. And are we done? Yes, we are done. Question 4 is done. Thank you for tuning in. Don't forget to like our videos and also subscribe to our channel. Until next time.
Well, welcome to MV Tutors. My name is Fikakahle Manana, and we are still doing paper 2 of the November 2022 examination. Okay, let's get right into it. It says 3 experiments A, B, and C are carried out to investigate some of the factors that affect the rate of decomposition of hydrogen peroxide. The balanced equation for the reaction is as given here. Identical samples of hydrogen peroxide are used in each experiment. The condition used in each experiment are summarized in the table below. Okay, I see ABC, temperatures, okay, AB are saying C is higher. Without catalyst, with catalyst, without catalyst. Now, question 5.1. 5.1 says, in which experiment A or B is the reaction rate higher? Use the collision theory to explain your answer. Well, it has to be B because it's got a catalyst. But now we just have to explain what happens with a catalyst. Okay, B with catalyst. Okay, so what happens with when you have a catalyst? The activation energy is lowered. Okay, activation energy is lowered. And then what happens if the activation energy is lowered? More what do I call these things? More molecules. Yes, more molecules have enough kinetic energy to make collisions. Okay, so they have enough kinetic energy. Where is all of this coming from really? Because remember, the graph looks like that. Okay, so when it's lowered, activation energy is lowered with a catalyst there. So now more molecules have enough kinetic energy over there. So now what happens when there's more kinetic energy? Effective collisions increase. Effective collisions increase. Okay. Okay, because there's more effective collisions, the reaction rate increases, because they asked in which of the two has a higher reaction rate. Reaction rate becomes higher. That's it. Let's now look at 5.2. It says the Maxwell-Boltzmann distribution curve X and Y for two of the above experiments are shown below. Okay, X is higher, Y is okay. Identify the curve X or Y that represents experiment C. So what happened with experiment C that's different? The temperature. Okay, so temperature increased. With an increased temperature, if you know your theory well, you could recognize that if you increase temperature on the Maxwell-Boltzmann distribution curve, you can see that the number of molecules will actually decrease. So it's Y. Okay, let's look at 5.3.1. Okay, 5.3 says the volume of oxygen gas produced in experiment B during the first 3.6 seconds is collected in a syringe as shown below. Write down the volume collected in the syringe. Okay, we can see it's in the middle there. So we basically have to get that value. You could use your head logic, but I rather, I prefer using sequences and series. Okay, so I'll say term 1 is 160, term 2 is 320, term 4 is 480. Now I want to test if term 2 minus term 1 is equals to term 3 minus term 2. Term 2 is 320 minus 160. Is that equals to 480 minus 320? What's this? This is gonna be 160. It's equals to 160 there. Okay, so what that tells me is that from there to there, from 480 to 640 is 160. And then the middle of it is, if I'm to actually calculate that, I will find that, let me just calculate it. It's 160 divided by 2, that's 80. And then I'm going to add that 80 to 480 so that I get that middle point there. Let me get my calculator. So it's going to be 480 plus 80, which gives you 560. Okay, so that then is the actual cubed. Okay, that's the reading right there. Let's take a look at the next question, which is 5.3.2 now. And it says the balanced equation for the reaction is that, cool. Calculate the mass of water that was produced during the first 3.6 seconds. Take the molar mass gas volume to be that at 25 degrees. Okay, so let's go. It's very important to get the right formulas that we can work with. So let's go to our formula sheet. So we'll take, because they want us to solve for what did the question want us to solve? It wanted us to solve the mass. Okay, so here's a formula with mass. We know number of moles is mass over molar mass. It also gave us a clue. It gave us this Vn. Okay, so let's take that formula down as well. Vm. Okay, all right, let's go back to the question. Okay, so it says calculate the mass of water. So from this formula, we know that the mass is basically number of moles times the molar mass when we're talking about water. Okay, but we have been given the molar gas volume for oxygen. Okay, So we can solve the number of moles of oxygen. The volume, we've just calculated it to be 560 right there. Okay, and then the molar gas volume is then 24,000. So we can solve, this is for oxygen, right? This is for oxygen. Okay, let's not get it confused. Cool. All right, let's get a calculator. So we'll say 560 divided by 24,000. Let's get it in decimal. Oof. Don't like that decimal. Let's leave it as 7/300. I normally don't like rounding off until the last part of it. Okay, so that's for oxygen. But now, when we look at our balanced equation, we know that between water and oxygen, 1 mole here is 2 moles there. Okay, you can see it there on the balanced equation. And now we have the number of moles of oxygen, which is 7/300, right? And we're looking for these ones, number of moles of that. So we're just simply gonna cross multiply, and I'll get that. X times 1 is equals to 2 times that. 2 times 7/300. Okay, so these are the number of moles of that. Okay, so let's put it 2 times 7 divided by 300, and we get 7/150. Okay, so these are the number of moles now of H2O. Okay, and they come from the number of moles of oxygen. Now let's look at our formula there. It's only missing the molar mass of H2O. Okay, so we know that H, let's go to our periodic table for this. Don't want to skip any steps. H is 1, and there's 2 of them, so I multiply by 2 plus O. I know it that it should be 16, but I just want to show you. There it is there. It's 16. Okay, now let's put that in a calculator. So it's 1 times 2 plus 16. And we get it's equals to 18. Now, if we go back to our formula now, where we saw for mass as number of moles times molar mass. Number of moles, 7/150 times the mass, molar mass of 18. Let's put that in a calculator. So now it's 7 times 18 divided by 150. What do we get? Only now can I round off. 0.84. What is it? Grams. Remember, mass is in grams. Okay, that's it. Let's now take a look at the next question. The graph below, not drawn to scale, is obtained for the mass of oxygen gas produced over a period of time in experiment A. Use the information in the graph to answer the following questions. Write down the rate of production of oxygen gas for the interval 30 seconds to 36. So there it is, 30 to 36, nothing's happening there. So my answer for 5.4.1 is 0. Okay, 5.4.2, will the rate of the reaction in interval 3 to 9, there's 3 to 9, be greater than, smaller than, or equal to the rate of reaction in the interval 9 to 20. Okay, so you can see it's steeper. So it has to be greater than, because it's steeper. Greater than. Okay, they don't ask for an explanation, but because the graph is steeper, that is why it's greater than. Let's look at the last question now, 5.4.3. Okay, let's give ourselves some space. It says the average rate of decomposition of hydrogen peroxide is that. Calculate the value of time t on the graph. Okay, so this is the rate. It's given in moles per second. So we've got number of moles and then we've got time. So that's a clue right there, which means we need to solve a number of moles first. Now, what do we have? We have, this is the mass of oxygen. So this will be for oxygen, O2. And we know that the mass at time t is already 0.9, as given in that graph, grams. And the molar mass of oxygen, remember oxygen is 16, and there's 2 of them, times 2. So we'll put that in the calculator. So we'll have 0.9 divided by 16. Let me put it in brackets rather. Let's put a bracket there. 16 times 2. Let's close the bracket. And we get 9 over 320. Okay, now let's look at the relationship between oxygen and hydrogen peroxide. There we go. We can see that from the balanced hydrogen peroxide and oxygen, we can see that it's 2 to 1 number of moles. And now here we have 9 over 320. We've got our x here that we're looking for. Okay, let's go back to our question. So it's x times 1 is equals to 2 times 9 divided by 320. That's what we put in the calculator. Okay, let's go ahead, pull up the calculator. I'm just gonna say from here, because I already have this answer, just gonna say times 2. Okay, and then I get 9 over 160. Okay, now that we have the number of moles of hydrogen peroxide, so what can we do with that? Remember the rate of hydrogen peroxide. Let me just put it here, H2O2 is equals to the number of moles over the change in time. Okay, because you can see it's given moles per second. So they've given us the number, the rate, which is 2.1 times 10 to the power minus 3. The number of moles, we've just solved them. It's 9 over 160. Okay, and that's divided by the change in time that we are actually looking for. So what I'm going to do is cross multiply and divide, so that we saw for change in time, it's going to be 9 over 160 divided by, if you do the gymnastics really well, 10 to the minus 3. Just bring this that side. Okay, let's get a calculator. We'll put the fraction on top there. We have 9 divided by 160. Okay, at the bottom here we have 2.1 times 10 to the power negative 3. Okay, what's our answer? Now I can convert to decimals. It's 26.79 seconds. That's time T. That's all. Please like and subscribe our channel if you learned something today. Otherwise, have a great day.
Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at the chemistry paper with you, specifically question 6. Don't forget to like our videos as well as subscribe to our channel. Please do spread the word to your fellow matric friends. Okay, people that you are studying with. Alright, so yeah, let's share information. Okay, we have you covered. We have a playlist with all the chemistry topics that are covered, as well as physics and maths. Okay, maths, our first love. So yes, question 6. Carbon reacts with sulfur according to the following balanced equation. So you have carbon in solid form plus sulfur gas, okay, and that gives us carbon disulfide. And we can see that the reaction, or rather, yeah, it is endothermic because our enthalpy is higher than 0. Alright, so now it says the system reaches equilibrium at temperature T in a sealed 2 cubic decimeters container. That is the volume they've given to us in cubic decimeters, which is perfect. If it were given in any other unit, you would have to convert it to cubic decimeters. Now it says the Kc value is 9,4 at temperature T. Alright, so basically the equilibrium constant. We'll see what we do with that value if we're going to use it. We might, we will. Alright, 6.1 says state Le Chatelier's principle. Okay, I'm going to state it. I'm not going to write it down because it will take some bit of time. But basically, when we look at Le Chatelier's principle, it's when you have equilibrium, okay, in a closed system that now becomes disturbed. Le Chatelier comes in and is like, hey, you just disturbed my equilibrium, so let us try to establish a new equilibrium. And how do we do that? And we do that by reinstating a new equilibrium by favoring by favoring the reaction that will oppose this disturbance. For example, you have an increase in the concentration of reactants. Okay, so that is a disturbance to the equilibrium that was. So if you're gonna counteract that and reach a new equilibrium, you will then increase the concentration of products. Okay, and then eventually you're gonna get a new equilibrium. Think about that seesaw example I spoke about in the lesson on our playlist. You can go have a look at it. Okay, so that's basically Le Chatelier's principle. If ever there is a disturbance to the equilibrium, a new equilibrium will be reached to counteract that disturbance. Okay, and in the case of increasing reactants, and then the counteracting part is increasing the products, so you will favor products in that case. Okay, so mention favor. Okay, mention which side is favored, and the side that is favored is the reaction that will cancel or oppose the disturbance. I spoke a lot. You have this in your textbooks, so let's just move on. Alright, 6.2. Now it says at equilibrium, 1 mole of carbon disulfide is present in the container. Calculate the concentration of sulfur gas present at equilibrium. Now let me remind you of the equation. So the equilibrium constant is the concentration of your products divided by the concentration of your reactants. And please make sure that only gases and solutions are participating. Everything else, solids, liquids, the value will be 1. Okay, so we don't include that. So what is the concentration of the products? Well, we have one product, which is carbon disulfide, and we're not going to include the concentration of carbon because it's a solid. That will just give us 1. However, we can include the one for sulfur because it's a gas, and we take it to the power 2. All right, the exponent there is 2, and we know that our Kc value in this case is 9.4. So let us write everything in terms of sulfur because that's what we're looking for. So if I now have the concentration of sulfur squared, that'll be equal to the concentration of carbon disulfide divided by 9,4. And if I'm looking for the concentration of sulfur, that is pretty much the root of carbon disulfide's concentration divided by 9,4. So what is the concentration of carbon disulfide? I'm going to just put it on the side here. Remember, concentration is number of moles divided by volume. We've been given that we have 1 mole, right? And the volume was 2 cubic decimeters, so we have a half concentration of carbon disulfide. So it is a half divided by 9,4, and all of that is rooted. Okay, so let us see there. We then have the root of 0,5 divided by 9,4, and we get 0,23 moles per cubic decimeters. Okay, it's noisy. I'm sorry about that. Yeah. Okay, now the volume of the container is now doubled at temperature T. After a while, a new equilibrium is established. So if we're going to double the volume, we went from 2 cubic decimeters. Okay, we started at 2 cubic decimeters and we're ending up at 4. Okay, so let's just note the change. So volume would now be 4 cubic decimeters. And then it says, how will the amount of sulfur change as this new equilibrium is established? All right, choose from increase, decrease, or remain the same. I'm not winning with the sound, but let's just continue. Okay, so now, if you're increasing your volume, remember that your pressure will decrease. All right, and if your pressure decreases, you're going to look at your chemical formula here. All right, without looking at the solid state, we're going to look at the gases because pressure relates to gases. So for sulfur, on the reactant side, I'm just going to put it there, reactants and products. From the reactant side, we have 2 moles. From the product side, we only have 1 mole. So now, whenever we're looking at pressure, okay, in this case, a decrease in pressure, you're going to look at where the number of moles are the most. Okay, and we can see that the reaction that will be favored is the reactants side. Okay, so your equilibrium will go in that direction towards the reactants, okay, to the left, towards your reactants. And so your reactants are favored and not your products because your products have the least number of moles. And that is how you test it for pressure. Okay, look at the number of moles. If you have a decrease in pressure, you'll know that where your number of moles are the highest, that is where the reaction is favored. If you had increase in pressure, you're going to look at where your moles are the least, and that is where the reactant or reaction will be favored. So in this case, it is reactant favored. It is reverse favored. Okay, so now, in this case then, the question is, what will happen to the amount of sulfur? Will it increase, decrease, or remain the same? Sulfur is a reactant, and as such, because this is reactant favored, it will increase. Alrighty, and then 6.4. Explain the answer to question 6.3 in terms of Le Chatelier's principle. It's basically everything I said. Like I said, if you ever increase your volume, you will have a decrease in your pressure. You have to look at your chemical formula and where you have the most moles. Okay, that is where the reaction will be favored. Okay, simply put. Okay, and now we get to 6.5. Okay, 6.5. Too much noise on the other side. Don't be surprised by the change in lighting and venue. Alright, so if the concentration of carbon disulfide changes by X mole per cubic decimeters, write down an expression for the equilibrium constant Kc in terms of X. Alright, and if you have a look, the mark allocation is 5. So you're not going to just write a simple equation. You have to literally use the rice table. Okay, and so what does the rice table consist of? Okay, so we're going to write everything in terms of moles initially. All right, and then we're going to change it over to concentration. All right, which will be mole per cubic decimeters. All right, so I left one venue with noise to another one with noise, so please bear with me. Yeah, there's no winning here. Unfortunately, if we have to wait for ideal conditions, work will not be done. So, okay. And then, let me do this. Yeah, so what do we have as our reactant? We have the sulfur, okay? And as our product, we have the carbon disulfide. Remember, we don't put in the solids here. It's just simply what will be put in the Kc formula. So the ratio now, if you have a look, there's for every 1 mole of carbon disulfide, you're actually going to get 2 moles of the sulfur. Okay, that is simply from the equation. That's where we take the ratios from. Now, initially, remember we calculated the concentration of sulfur at equilibrium and we got 0.23, and the volume at that point in time was 2 cubic decimeters. So in order for us to get the number of mole will simply be concentration times volume. So concentration 0.23 times 2, you're going to get 0.46, okay, mole. And you had initially 0.5 mole for carbon disulfide. If you're going to multiply by 2, you're going to get 1 mole. All right, and I think that information was given, yes, at equilibrium 1 mole. So that's cool. Now the change, they tell us that the concentration is X. That's the change. But we're looking for the number of moles. And remember now, the volume is now doubled. So instead of 2 cubic decimeters, we have 4. Okay, I wrote 4 down at some point because I was wondering where we're going to use it. Now here we are. Here we are about to use it. Great. So to get the number of moles now for the change, that'll be 4x for the carbon disulfide, okay? And I remember for every mole of carbon disulfide, we get 2 moles of sulfur. So it will be multiplied by 2, and we're going to have 8x, okay? Now, at equilibrium then, remember, because of the increase in volume, the pressure decreased and the reactants were favored, okay? As such, we're going to be adding on the reactant side and subtracting on the product side. Okay, so 0.46 plus 8x. We don't know what x is. So, and they did say don't solve for it. No need to solve. Just write it in terms of x. So now this side we have 1 minus 4x. Perfect. And now we need to get our concentration in terms of moles per cubic decimeters. Okay, currently we have it in terms of mole. And remember, because the volume is 4, we're going to divide just by 4. So 0.46 plus 8x is divided by 4. I mean, you could have simplified it and said 0.46 divided by 4, but, you know, let's just leave it. Now we can get to the Kc. Okay, we're going to write Kc in terms of x. And remember, the concentration, Kc value, equilibrium constant will be the concentration of your products divided by the concentration of your reactants. All right, and we have them over here. The product will be calcium disulfide and your reactant will be sulfur. Okay, so the concentration of calcium disulfide to the power 1 over the concentration of sulfur to the power 2. All right, and then we have the concentration. Yes, we do. It is 1 minus 4x over 4, and that is divided by 0.46 plus 8x all over 4, and that is squared. Oof. Whoa. Okay, so they want no simplification. Oh, hallelujah, no simplification, because wow. Okay, if there's no simplification, I think let me just write it in fraction form. Okay, because I thought now I'm gonna have to work it out and simplify. Yo, that was gonna be a long one. Okay, let's go back. So we have 1 minus 4x divided by 4 divided by 0.46 plus 8x all over 4. And that is the Kc value, guys. We don't need to, they have relieved us from simplifying it, so I'm happy. I hope you are too. But remember, we need to square the concentration of the sulfur, and also remember they gave us the Kc value at temperature T, and even when the container, the volume was double the temperature T, we still have the Kc value of 9.4. So 9.4 is equal to all of that. Concentration of your carbon disulfide divided by the concentration of your sulfur squared. Okay, now we are officially done. All right, 6.6. The reaction rate time graph below represents further changes made to the equilibrium mixture. The volume of the container is kept constant. Okay, so nothing done to pressure in this case, all right? Volume is constant, meaning pressure is also constant. So we see that the forward reaction is represented by the solid line and the reverse reaction is represented by the dotted line, all right? And then now getting to, so this is question 6. Now question 6.6. Okay, 6.6.1. What do the parallel lines between time A and time B represent? Okay, so whenever you have a horizontal, because they could have been parallel and at an angle. So as long as they are horizontal and parallel to one another, it means that the equation had reached equilibrium. Okay, or the reaction, not equation, the reaction had reached equilibrium. Okay, so that is where equilibrium is seen and reached. Okay, and what is equilibrium? Basically, the forward reaction, the rate of the forward reaction is equal to the rate of the reverse reaction. All right, so that is your equilibrium that has been reached. All right, you could even say chemical equilibrium. This is a chemical reaction. And now 6.6.2, what change was made to the equilibrium mixture at time B? Okay, so you see there is a sharp increase in the forward reaction, and in your forward reaction you see that you have sulfur over there, which then ultimately gives you carbon disulfide. Okay, so I would say that the sudden change made to the equilibrium mixture, there could have been an increase in the concentration of sulfur. Okay, yes, there could have been increase in the amount or concentration of sulfur. So increase in the concentration of sulfur. Okay, can you think of something else? You can write it down on the comment section. Okay, let's interact. All right, and then 6.6.3, give a reason for the sudden change in the reaction rate at Tc. Okay, time C. So we can see that both the reverse reaction and the forward reaction, the reaction rate actually decreases. In this case, guys, we actually have a decrease in temperature. Okay, it affects both the forward and the reverse reaction. All right, 6.6.4, fully explain the answer to question 6.6.3. Why are we saying that there is a decrease in temperature? Okay, first of all, we can note that the rate of the forward reaction, I think let's just write it down. So the rate of the forward reaction and of the reverse reaction actually decreases, both of them. Okay, the rate decreases. Please follow me, I'm gonna use symbols and signs. Okay, but look at the forward reaction rate, it decreases more. Okay, and remember the forward reaction is endothermic. right? So yes, we are sort of not surprised that the forward reactions rate or reaction rate decreases more. Okay, so the rate of the forward reaction, okay, decreases even more. All right, why? Because it's an endothermic reaction. Okay, endothermic reaction. All right, and then yeah, and then finally we would then say a decrease in temperature would actually favor the reverse reaction, because the reverse reaction is exothermic. Okay, so yeah, so this decrease in temperature favors the reverse reaction. Okay, and that is why you see that you have a higher value or higher reaction rate for the reverse reaction. I don't know if you can see my cursor, just a little dot. Yes, hence you have that for a higher rate of reaction for the reverse reaction more than the forward reaction. But yeah, those are the answers I would give for those 3 marks. And that concludes question 6. What a ride.
Well, welcome to MV Tutors. My name is Firagasha Manana, and we are still doing the 2022 Physical Science Paper 2, the chemistry part. We're now in question number 7, so let's get right into it. Ethanoic acid is a weak acid that reacts with water according to the following balanced equation. So they give the equation to us. First question, define an acid in terms of the Lowry-Bronsted theory. Well, this one, I'm sure you've seen it so many times because they love this question. Okay, it's just simply an acid. An acid is a proton donor. That's it. That's all you have to say. Proton donor. Okay, right there. Okay, second question. Give a reason why ethanoic acid is classified as a weak acid. Well, they're basically just asking us to define what a weak acid is, and it's an acid that does not dissociate completely. So, does not dissociate completely. Just like this. Completely. That's it. Okay, let's try the third one now. 7.1.3. It says write down the formulae of the 2 bases in the equation above. So if you look at the left hand side, oh, that's definitely an acid right there. See it? Which means that water is a base. Okay, that's what they want. So H2O, and let's come look at this side now. Okay, so H3O is definitely an acid right there. Can't be anything else, because remember what an acid anyway. So if that's an acid, then this is a base. So these are conjugate bases and acids, and we're just interested on the acids at this point. Well, that's just it. All right, let's look at question 7.2 now. Let's go 7.2.1. So it says a flask contains 300 centimeter cube of water of dilute sodium hydroxide. There we go. Of concentration 0.167 moles per decimeter cubed. Okay, that's important. Anyway, they say calculate the number of moles of sodium hydroxide in the flask. Now, we have to go look for an equation of number of moles that has concentration and volume. And we know that number of moles is equals to concentration times volume. So the concentration is 0.167 times the volume. Remember the volume you were given in centimeter cubed. to convert it to decimeter, because we have to be consistent, we have to divide by 1,000. Okay, so this is what we're putting in the calculator. That's the whole tricky part about this question. So it's 0.167 times 300 divided by 1,000. Okay, and then we get, so the number of moles is 0.05 mole. Okay, that's it. Okay, let's look at the second question now. It's 7.2.2, and it says ethanoic acid of volume 500 centimeter cube and an unknown concentration X of an unknown concentration is now added to this flask to give a solution of volume 800 centimeter cube. It is found that the pH of this mixture is 11.4. The balance equation for the reaction is that calculate the concentration of OH in the mixture. Okay, first of all, we know that pH plus POH is equals to 14. And then we're given that the pH, and we're looking for the OH concentration, right? So the pH, we're given that it is 11.4 plus POH is equals to 14. So at this point, we just do mathematical gymnastics. We take this 11.4 to the other side. Let's do that right now. So it's gonna be 14 minus 11.4, and we get an answer of 2.6. So 2.6, that's our POH. Remember, that's POH. We still need to calculate the OH concentration. Now, we know that the formula of POH is actually equals to the minus log of the concentration. Okay, and the concentration is what we're looking for. So let me just put the numbers. We have that's 2.6 is equals to minus log OH, which is what we're looking for. From this point, it's just gymnastics as well. If you remember your relationship between logs and exponential functions, that's their inverses of each other. So the base of a log, okay, is, if it's not given, it's always going to be 10. Okay, and then the base of the log is the base of the exponent. Okay, so what I'm going to do is then take this 2.6, put it on top there, 6, and so the concentration is this side, and remember I have a negative there. Okay, this negative is movable. It can move on top of, it can move up here. Remember, these are just laws of exponents. It can move up there, and then once it's there, okay, let me just solve this right here. Let's get a calculator, and then we're gonna have 10 to the power 2.6, and then we get a big number of 398.11. Okay, but I don't like this number. Remember, this is equals to the minus. Okay, and this, what this is really is 1 over, we're just doing first principles there, 1 over OH, okay, is equals to this 398.11. and then to get the OH on its own, I'm going to cross multiply, okay, such that if I do that, I will have OH this side, and then I'll have 1 over 398.11. That is my real OH. Therefore, the concentration, if I just put this in a calculator, is 1 divided by 398.11. Okay, and then I get concentration is equals to 2.51 times 10 to the power minus 3. And concentration is in mole per. If we look at the things that we're dealing with here, per decimeter, remember it's per decimeter. Okay, so per decimeter. I'm running out of space, sorry, but that's pretty much it. Thank you so much. Okay, we're gonna look at the next question now. It's actually the last question, 7.2.3. It says calculate the initial concentration X of the ethanoic acid. Okay, so first of all, let's start here. Concentration, what's the formula? C is equals to number of moles over V. Now let's check. Do we have the number of moles of ethanoic acid? No, we don't, which means we need to calculate them. Do we have volume though? We do have volume. We're given 500 centimeter cubed. Okay, so let's go calculate the number of moles. Now, the nice thing about this is that when it comes to number of moles, they all share them according to ratios. So we can use what we've been given and what we do have to solve the number of moles for any of these balanced equation variables, or rather elements. So we have a bit of information about OH, which has to do with the sodium, as you can see there. So what we're going to do is calculate the number of moles then of that. Okay, the number of moles of sodium hydroxide. That's an A and that's an OH. Okay, so we'll take, remember, its concentration, just to put it there, its concentration times a volume. And the concentration we're working with is this 2.51 times 10 to the power minus 3. We calculated it right over there. And then the volume that we're working with is this new volume, okay, which is 800 divided by 1,000 to convert the centimeter cube to decimeter cube. Okay, let's bring calculator now. So we're going to say 2.51 times 10 to the power minus 3. We go downstairs times 800 divided by 1,000. Okay, there we go. And then we get this answer here, that it is 2.0, let me say 0.1 times 10 to the power minus 3. Okay, but now we want the number of moles, because this is the number of moles in the mixture. But we want the number of moles that are actually reacted, if I can put it that way, reacted. And to get that, we need the initial number of moles minus these ones that are in the mixture right now, which is what is left, essentially. So the original one, we calculated it, there we go. The number of moles was 0.05, calculated it in that question. So these questions are definitely connected. So it's 0.05 minus this, what we just calculated, 2.01 times 10 to the power minus 3. Let's put that in a calculator. We get 0.05 minus 2.01 times 10 to the power minus 3. Okay, so now we get that it's 0.048. Okay, more. All right, So now we have the number of moles and we have volume. We can now calculate the concentration. So the number of moles is 0.048 divided by the volume. We spoke about it, that the volume of ethanoic acid alone is 500. But I'm gonna divide it by 1,000 in order to convert it to a proper concentration in decimeters. Okay, now let's get our calculator. So I have a fraction, it's 0.048, and then we go downstairs, we put 500, we put the sign, divide by 1,000. And then that's our final answer, 0.096 mole per decimeter cubed. Now this is the concentration, or rather, let me not say the concentration, but rather the X that we were solving for. Okay, that's the initial concentration that we are interested in. Well, that's it. Thank you so much for watching. Please like and subscribe to our channel. We would really appreciate it. Enjoy the rest of your day.
Hello everyone and welcome back to MV Tutors. We are continuing with the chemistry paper and we are looking at question 8. We are almost there. All right, so it says, let me just shift my face. Where is it going? All right, so a piece of zinc is placed in a test tube containing an acidified permanganate solution. All right, after some time, it is found that a redox reaction has taken place. Okay, so something has been reduced, another thing has been oxidized. So now use the table of standard reduction potentials to answer the following questions. Alrighty, let's just shift it back. And now let's get to 8.8.1. No, 8.1.1. Alright, so it says, write down the name or formula of the reducing agent. Now, what is the reducing agent? The reducing agent is the one that has been oxidized, meaning it has lost electrons. And looking at zinc and looking at permanganate, which one is more likely to be oxidized? Let's go have a look at the table. I mean, they did refer us to it. They did say that, hey, go have a look at the table of the standard reduction potentials. So I'll go with this first one, table 4A. All right, and then zinc should be somewhere at the bottom. So I hope you see zinc over there, which is negative 0.76. Remember, when you're looking at this table, it is placed such as, if they say standard reduction potential, what is more likely to be reduced? So at the top of it, fluorine is the one that will reduce the most, okay? And lithium is the one that will be oxidized. Okay, so zinc definitely will be oxidized. Let's go look for, oh, by the way, here is zinc. Yeah, okay, but zinc, I hope you can see it. Here it is. Zn has negative 0.76. It is more likely to be oxidized, hence it has a negative value. Let's go look for permanganate, and I hope you see it over there. Okay, it is more likely to be reduced. Okay, so zinc is more likely to give away the electrons, like go away, I don't really need you. Okay, let's go back then to question 8, and the train is coming. So 8.1.1, it is zinc. Okay, please just bear with me through the noise. Well, 8.1.2. Refer to the relative strengths of the oxidizing agents to explain why a redox reaction has taken place. So we did have a look at the table, right? And what did we notice? We noticed that the permanganate solution is high up in the table, all right, meaning it is more likely to be reduced, and zinc is more to the bottom, so it'll be more likely to be oxidized. So in this case, then, when we write this answer, so 8.1.2, we say that the permanganate solution Oh, it's raining. So the permanganate solution is a stronger oxidizing agent. It's a stronger oxidizing agent than your zinc 2 plus ions. Okay. Therefore, so permanganate is strong oxidizing agent than zinc ions. Therefore, it will oxidize the zinc into the zinc 2 plus ions, because zinc is more oxidized than the permanganate. It loses 2 of its electrons and it's left as zinc 2 plus. 8.2. A standard electrochemical cell is set up as shown below. So we can see we have a voltaic cell or galvanic cell, and we have our nickel ions as well as our manganese. Did they tell us which one is the anode and which one is the cathode? They didn't. Remember, at the anode, that is where oxidation occurs. Okay, NOx. And at the cathode, that's where reduction occurs. Okay, so red cat. So let's go have a look at the standard reduction of potentials, the table, and see between the two which one is more likely to be oxidized and which one is more likely to be reduced. All right, so nickel, manganese. Let's go, let's see. Okay, where is nickel and where is manganese? Starting from the bottom. So manganese is more likely, well, there's manganese, where's nickel? Nickel is up there. So manganese is more likely to be oxidized. Okay, so that's where manganese is. And nickel is up there. It is more likely to be reduced. Okay, so we can go back to our question and then see which one is the cathode and which one is the anode. All right, so we know then for nickel, we have the cathode, and we're normally used to the cathode being on the right-hand side. So please, when you get a sketch, do not assume that every time on the right-hand side you have the cathode. It can change. So where nickel is, that's where you have the cathode. Where manganese is, you have the anode. Sorted. Okay, let's now go and answer questions. So 8.2.1, write down the function of component Y. Y is the salt bridge. What does the salt bridge do? In simple terms, it completes the circuit. Okay, allows the flow of electrons. So it completes the circuit. If it wasn't there, you wouldn't get a reading on the voltmeter. Or you could, but nothing would happen. Nothing would be reduced. Nothing would be oxidized. So you need that salt bridge to complete the circuit. Okay. And then 8.2.2. In which direction will electrons flow in the external circuit? All right. So it will flow from the cathode. No. It will flow from the anode. What am I saying? It will flow from the anode to the cathode. And at the anode, that's where you have manganese. Okay, so it go from manganese to nickel. All right. And now 8.2.3. Calculate the initial EMF of the cell. Why didn't we write down the values? It's okay. It's all right. Let's go back. So now let's have a look at the formula. So we're going to say the EMF is equal to, you can choose any one. I prefer using the cathode minus the anode. It's really up to you. And then for the cathode, we know that's where we have nickel. So let's go have a look at the table of the standard reduction potentials. Cathode, we have nickel. Where is nickel? There it is. So nickel is negative 0.27 minus manganese. There it is down here. So it's negative 1.18. Okay. And if we use the calculator, it's a simple sum, but some of us still need to use the calculator. We don't want to take risks. Negative 0.27 minus negative 1.18. I left it in scientific notation. So it's basically going to be 0.91. If it's 9.1 times 10 to the negative 1, we just take that decimal to the left. So it's 0.91. Don't forget the unit, which is volts. Alrighty, so we are flowing here. Let's get to question 8.2.4. All right. So it says, write down the balanced equation for the net cell reaction taking place. Yeah, okay. So we're going to talk about what happens at the anode and what happens at the cathode. Okay, I'm just going to put the anode and cathode. All right, at the anode, that's where we have manganese. At the cathode, that's where we have nickel. All right. And what are we going to start with? Let's go back to the table, our standard reduction potentials. Okay, so at the anode, that's where oxidation occurs. The cathode, that's where reduction occurs. And at the cathode, that's where we have our nickel, right? Yes. So the way it's written, all right, whenever there's reduction happening, you're going to write down the equation as it is from the table. So at the cathode, you have nickel, 2 plus 2 electrons, and please, one arrow, not two of them, and you have your nickel, okay, solid. I don't know if they want the states, just put it just in case, the phases I mean. And then at the anode, that's where you're gonna have manganese. Sorry guys, my nose is so itchy. So you have manganese, and we're gonna reverse the formula. Okay, you're gonna start with the manganese. Now I want to write magnesium. So manganese. And then we have manganese 2 plus 2 electrons. Okay, so this is solution. Alrighty, and then fortunately for us, the electrons are balancing. Okay? So because they are balancing, that is great. We don't need to balance anything. We can just write down. Wait, what was the question again? I'm busy here writing things. Now I'm forgetting what the question is. The question is the balanced equation for the net cell reaction. So when we do write down the net cell reaction, this is what we're going to do. This is how we're going to write it. So I'm just going to put some 2 solid lines. Okay. So now we have manganese plus nickel, 2 plus, and we don't have to put in the electrons this time when we write the net cell equation. So we have manganese 2 plus in solution plus nickel. And that's it. I think this should be our equation. Okay, so it's balanced and the train is making a whole lot of noise. Alright, and the last question. Okay, so it's only 1 mark. 8.2.5. It says the concentration of nickel 2 plus is now increased. Okay, oh, there's one thing I wanted to make a comment that I forgot. Whenever you calculate the EMF of a voltaic cell, please make sure you get a positive answer. Because if you get a negative answer, then your calculation is either wrong or you're looking at an electrolytic cell. Okay, so please make sure it is a positive answer. Okay, let's move on. Okay, 8.2.5, the concentration of nickel is now increased. Okay, will the reading on the voltmeter increase, decrease, or remain the same? Guys, I covered it. It's only 1 mark and I'm going to give you one answer. If you want to know why, go look at our playlist, go under voltaic cells, and I explain it quite nicely, talking about reactants. If you increase the reactant, what happens? If you increase the product, what happens? So yeah, go check it out. But it says the concentration of nickel 2 plus is now increased, okay, which is part of the reactance, hint, hint, will the reading on the voltmeter increase, decrease, or remain the same? The answer is increase. And why is that? Go look at the playlist. And I'm going to say goodbye with that. So we're done with question 8. See you at question. Hello everyone and welcome back to MV Tutors. I'm Telo and we are finally doing the last question of this chemistry paper. It has taken quite a while, but we're here. So let's get to it. Please don't forget to like our videos and subscribe to our channel. Alrighty. So the diagram below represents a simplified cell used for the electrolysis of concentrated chromium chloride. Alright. Electrodes R and T are made of carbon. Okay. You can go through our playlist, chemistry playlist, if you want to know more about galvanic cells, voltaic cells, as well as electrolytic cells. And here we have an electrolytic cell. Okay, so question 9. Let's start answering the questions. So we have the net cell reaction. They were generous enough to give it to us. Alright, and then 9.1 says or asks, define the term electrolysis. Some say electrolysis, it's up to you. So basically it's a chemical process in which electrical energy is converted to chemical energy. So yeah, so it's a chemical process first of all. And what happens in this chemical process? We have electrical energy converted to chemical energy. Okay, so what? 2 marks. That's a nice 2 marks to get. Alright, question 9. The graph below, not drawn to scale, represents the changes in the mass of electrode T during electrolysis. Electrolysis. Whatever. So yes, we can see that the mass of the electrode T increases with time. That is a clue. What's happening there? Is it reduction that's happening or is it oxidation? Remember, oxidation is the loss of electrons, whereas reduction is the gain of electrons. So looking at this T, actually that is where reduction occurs. That is the cathode. We can safely assume that. But anyway, it says write down the half reaction that takes place at electrode T. Okay, so we're going to go and go to the reduction potential table of reduction potential and get the half reaction. But what we're going to get ions plus some electrons, and the answer will be a solid, okay, because the mass is increasing. Okay, so let's go have a look at chromium over there. Table 1. Ooh, I see it. I don't know if you can see it. I can't write on the PDF, but chromium 3 plus. Okay, we're gonna write it exactly as it is because that's the reduction. That's the table that we're getting. It is in the form of reduction. If you wanted to do oxidation, you would have to swap the things around. Okay, so we have chromium 3 plus. Okay, and it's, I don't know if they want us to write down the phases, but I think it's safe to write down the phase. Yes, chromium 3, you have 2 of them. Yo, do you see that? There's chromium 3 plus 1 electron. We're not dealing with that. We're dealing with chromium 3 plus with 3 electrons. Okay, and then you, with 1 arrow, not a double arrow, we're going to get the chromium solid. All right, I think out of interest, maybe you can write it for yourself because you never know if you're going to need it. That the reading on it, the EMF is negative 0.74. Okay, volts. Like I said, you don't really need to write it down. I don't know what the next questions are. I don't want to have to come down to this table all the time. All right, so now we're done with 9.2.1. Okay. Oh my word, looks like this paper is something. Okay, I think maybe this is 9.2.2. Alright, so it says a current of 2.5 amperes passes through the cell for 10 hours. Okay, so let's just write down what we know. The current is 2.5 amperes, passes through the cell for 10 hours. We normally use seconds. So 10 hours multiplied by 60 minutes multiplied by 60 seconds. Okay, I have the calculator, but this is like what, 3,600? So we have 36,000. Okay, let me just make sure. So 10 times 60 times 60. So yes, 36,000. 1, 2, 3, 4. Yeah. Okay, cool. So that is the seconds. That's the time. Now it says calculate the total charge that flows through the cell during this time. Okay, guys, something is missing in this paper. Okay, so anyway, let's start with 9.2. I'm assuming this is it. I don't know if there's another question after that. And then value of x as shown in the graph. Okay, I need to look for another paper. But anyway, let's just see. So a current is passing through it. We have the current, we have the time. Calculate the total charge. Oh yeah, okay, x value at 10 hours. Okay, it's cool. We can calculate the total charge, it's okay. If you've forgotten, is it going to be here? No, it's probably on the, oh, there it is. Q is equal to I delta T. So the current is 2.5 and delta T is 36,000 seconds. All right, and if we're going to use the calculator, so 36,000 times 2.5 and we get 90. Or we can just say, write it down as in scientific format since we have it, 9 times 10 to the power 4 coulomb. Okay, or 90,000. No, it's all good. Are we done? This was so short. Really? Wow, okay. Wow, all right, I'm shocked. We're done. We're done, guys. We're done. Thank you so much for tuning in. Have a lovely day further. Don't forget to tell your friends about our YouTube channel. Thank you for those who have subscribed. We are seeing the numbers are growing. We really appreciate it and we want to serve you more. We'll see you next time with maths. Hello everyone and welcome to MV Tutors. I'm Solo and I have received comments that I actually didn't finish the paper. The question paper that I had didn't have the last numbers, so I honestly missed 9.2.3. Completely sorry about that, but here we are and I'm here to fix that mistake and we're gonna just do it. So thank you for those who commented and told me that 9.2.3 is missing. We're going to do it now, so I really apologize. So 9.2.3 says we should calculate the value of x as shown in the graph. Okay, so remember, x is the mass of electrode T. And electrode T is basically where reduction occurs. That is the cathode. Okay, red cat. And we know that the initial mass of the electrode, just the electrode itself, is 2.2 grams. Now, as the chromium is being reduced and forming around this electrode, the mass will increase, which, we're going to get to x. So that is basically what we're calculating here. So let us see, 9.2.3, just going to start it over here. So what do we know so far? So from the previous question, we were able to calculate the charge, all right, that flows through the cell during this time, okay? This time of 10 hours, that is. And what we can do then, we can then say, let's find out how many electrons, number of electrons that chromium actually has. Let me actually do this. Yeah, number of electrons for chromium. It'll basically be the charge that we calculated previously and the charge of an electron. All right, so the charge that we calculated was 9 times 10 to the power 4 divided by the charge of an electron, which is 1.6 times 10 to the power negative 19. I hope I have remembered it clearly, and we're just going to calculate quickly how many electrons chromium has. And what are we going to do with the number of electrons? Well, basically from there, we want to get the amount of atoms. And for us, to get the number of atoms, we are going to remind ourselves that for chromium to be reduced, it had to gain 3 electrons. So to get the number of atoms, we're going to divide by 3. Okay, but let me not jump the gun. Let's just take it step by step. So we have 9 times 10 to the power 4, and we're going to divide it by 1.6 times 10 to the power negative 19. This calculator. Okay, let me just set it quickly to scientific notation. Let me pause. Alright, I got it. So it is 5,625 times 10 to the power 23, and those are the amount of, that is the amount of electrons that we have for chromium. Alright, and now I said, what are we going to do with these amount of electrons? Like, now we're going to get the amount of atoms, and you're going to see why we need the amount of atoms. Okay, so now we have all of these amount of electrons. 5,625 times 10 to the power 23, and we are going to divide by the amount of electrons that were gained, which were 3. So 3 electrons, and let's just see what the answer would be there. So we're going to divide all of this by 3. So we get 1,875 times 10 to the power 23. Alright, and that's the amount of atoms. And while you're here, you're like, okay, still don't get what we're doing. We're going to take these amounts of atoms and we're going to use the Avogadro's number so that we can get the amount of moles. And once we have the amount of moles, we can use our molar mass to get the mass. Okay, so you see where we're going, what the vision is. Alright, so we have the number of atoms. Now let's get the amount of moles. So number of moles for chromium would be the number of atoms that we just calculated, 1,875 times 10 to the power 23, and we're going to divide it by Avogadro's number. It is there in your formula sheet, 6,02 times, I think, 10 to the power 23. Let me just check in my textbook quickly. Okay, yeah, so it is times 10 to the power 23, and the units. Okay, so we have atoms. So here we have atoms per mole. Alright, so you guys are used to writing it like this, atoms per mole. Alright, now let's see how many atoms we have. Calculator. So that divided by, so we have our answer divided by 6,02 Avogadro's number times 10 to the power 23. And we have 3,11. Let's round it to 3 decimal places just to be safe. So 3,115 times 10 to the negative 1. And that is the number of mole. Alright, so now we know our formula. We have number of moles is the mass over the molar mass. Okay, and if we want the mass, that will simply be number of mole multiplied by molar mass. So the number of mole, we've calculated it. It's 3,115 times 10 to the negative 1. And the molar mass. So the molar mass, you're going to look for it on your periodic table. Okay, so chromium. I think it has mass numbers at 52 or 53. 52. Okay. So you see, I have an image here. I don't have the actual paper, so I can't check with you, but you have it yourself. Alright, and so we're going to go back to our calculator, and we're going to multiply by 52. Okay, so times 10 to the 1 just means we're going to take the decimal and shift it 1 place to the right. So we're going to get 16, 16, 16,20. And that is the mass, that is the grams. Okay, but we're not done, because what we have calculated is just the mass of the chromium that has formed around the electrode. They want the mass of the whole electrode, so we need to add that 2.2 grams for the original, just the electrode by itself. Okay, So you had the electrode over here, and you know it started to gain weight when chromium was all attracted to it and it was reducing all over it. Okay, so this is the 2.2 and this is the 16.2 that we just calculated, but X is a combination of both. So the mass of X, right now it's the mass of chromium alone, the mass of X is 16.2 plus 2.2. Okay, we don't need the calculator for this now, we can just calculate it. And as we see, so we have 18,4 grams. So yeah, that's it. Sorry that it took this long, but it's done, and I hope it helps you, and I hope that you understand much better. So yeah.